going to look more generically at functions, and we're going to look at just polynomial functions. So we've talked about in particular linear functions and quadratic. Now I'm going to give you the definition of any polynomial function. A polynomial function of degree n is a function whose rule is a polynomial of degree n. So this is really saying that all polynomials are functions. If your rule is a polynomial, then that is a function of the same degree. So just a couple of examples. If I have the function 3x minus 2, the degree of my highest x power is 1. So this has a degree of 1. If I have the function 3x squared plus 4x minus 6, the highest degree is 2. If I have x to the 4th plus 5x cubed minus 6x squared plus x minus 3, that has a degree of 4. So to indicate the degree of a polynomial function, you just look for the highest power on that function. So we're going to explore something with these called end behavior. End behavior basically tells us what happens on the ends of the graph. So we're going to consider the graphs of f of x equals ax to the n. So that's any polynomial function where a is a real number and n is a natural number. So first example graph here, if I have, let's say, a polynomial that looks like this, that has an a value that's greater than 0 because it's opening upward, and it has an n value that is even. I know it is even because both ends of the graph open up. So this could be an x squared function. It could be something like 24x to the 6th. It could be 7x to the 14th. Any number that has a positive a value and an even exponent. So switching to one that has an odd exponent, maybe something like this, we know it's odd because the ends go in the opposite direction. So odd for opposite. The a value is still positive because the right side goes up. So we focus on the far right side. If it's going up, my a value is positive, but the power is odd because the endpoints go opposite direction. So this could be x cubed. This could be 1/5 x to the 7th. This could be 10x to the 31st. Anything that has a positive a and an odd exponent. Okay, now we're going to focus on if our a value is negative. So this would be an a value that's negative, but our n is even. And it's even again because the endpoints match and go in the same direction. So this could be a negative x squared. This could be negative 1/12 x to the 6th. Anything that has a negative a value and an even exponent. Okay, and then a negative a value with an odd exponent will be our last example here. Could look like this. So I know that a is negative because when I look at the right hand end, it's going down. and n is odd because the ends go in opposite directions. So this could be like negative x cubed. This could be negative 5x to the 7th. Anything with a negative a value and an odd exponent. So we're going to use this to match equations or functions to their graphs. So a couple of other things to know. Higher degree polynomials have peaks and valleys. That can be found for us using a calculator, or you can use calculus. If you know calculus, you can find the maximum and the minimum, which are these peaks and valleys of your polynomials. The main thing we want to focus on is the total number of peaks and valleys. This number is at most, it's important that you recognize at most n minus 1. And the number of x-intercepts is at most n, where n still it represents our degree. So if I have something that's degree 4, it can have 3, 2, or 1 peaks and valleys, and it could have up to 4, so 1, 2, 3, or 4, or 0 x-intercepts. Your polynomial graphs are always smooth and continuous. Meaning there are no gaps, breaks, corners, or sharp turns. On polynomial graphs, the domain will always be from negative infinity to positive infinity, or all real numbers. And when the value of x is large, the end behavior mimics the largest degree term. In the polynomial. And move swiftly away from the x-axis. Okay, so we're going to look at a couple of examples. If I have the function 1.5 x to the 4th plus x cubed minus 4x squared minus 3x plus 4. You can graph that in your calculator. I did that ahead of time, and I'm going to show you what that graph looks like. I'm just doing a rough sketch, so not anything that's meant to be super accurate. This is the graph of this function. So if I focus just on this highest degree term, it has a 4. So that means the most I can have at most 3 peaks and valleys. Okay, I'm going to mark those with a blue dot. I have 1 valley, a peak, and a valley. So 2 valleys and 1 peak for a total of 3. And then it can have at most 4 x-intercepts. Now this one only has 2 x-intercepts, but at most means that many or fewer. So it still fits that. And then notice it's even and positive a value. So the ends both go up in the same direction because of the even nature. Then the 1.5 is what tells us it goes up instead of down. Okay, next one is x to the 5th minus 5x cubed plus 4x. Here's my sketch of that, copied from a calculator. Okay, so again, the x to the 5th term really determines most of our behavior. It's an odd, so they go in opposite directions. The a value is a positive 1, so up and to the right on the end. We could have at most 4 peaks and valleys. So if I count those, I have 1, 2, 3, 4. I have the most I can have. And then I can have at most 5 x-intercepts. So I have 1, 2, 3, 4, 5. I have all 5. So this is an example that's maxed out what our possibilities are. So you can use that information in your assignment. You're going to be asked to match some equations to their graphs, and you're going to use this idea of end behavior, the number of peaks and valleys, and how many x-intercepts it could have. And then we're also going to talk about something called multiplicity. Multiplicity is the number of values for which a given condition holds. If multiplicity is even, the peak or valley is tangent to the x-axis. And for a point to be tangent to the x-axis means that it just touches the x-axis and moves away. If multiplicity is odd, the graph passes through the x-axis. Okay, so we're going to apply this to our next example. We're going to find the zeros and the multiplicities. Then we'll sketch the graph. So I'm going to give you the function in factored form. If it's not given in factored form, you would need to factor it. So once it's factored, the zeros would be where each of the factors equals 0. So I set each of those factors equal to 0. Solve for x. And then to determine the multiplicity, I look at the exponent on the factor. So x minus 1 is only in my factored form one time. That has a multiplicity equals 1, which is odd. So the graph will pass through the x-axis at x equals 1. X equals -3 came from x plus 3, which is squared. So it has a multiplicity of 2. The graph will be tangent at that point. At x equals 6, that came from a cubed term. So we have a multiplicity of 3. So our graph is going to pass through. And then x equals -1 came from x plus 1 squared. So multiplicity is 2. The graph will be tangent there. So we're going to use that information to completely sketch this graph ourselves. We really don't know what it looks like, but we have some basic information we can take advantage of. So I know I have x-intercepts at as far down as -3, at -1, and then all the way up to 6. So I have 1 and 6. So to use the information from the previous part, when I talk about the peaks and valleys or the end behavior, if I add all of the exponents that were given here, the sum of the exponents, I have 1, oops, forgot my equal sign, 1, 2, 3, and 2. So that would be 5 plus 3 for a total of 8. And I don't have any negative a value here. So both ends are going to go up because I have an even power. So I know that my graph is going to, let's look at my first negative value, -3, sorry, at -3, the graph is just tangent. And then I'm at the end of my graph. So my graph should go up. And then it should just hit -3 and go back up. At -1, it is also tangent. So I'm going to do some kind of movement up here and then just go tangent and go back up again. At x equals 1, my graph should pass through. So I'm going to do like that. And then it passes back through at 6, giving me a graph with both ends up, as it should be according to end behavior. Okay, finally we're going to look at a regression on a higher order function. So we have the following table that shows revenue and cost in millions for the Ford Motor Company. We have the years from 2004 to 2012. We're given the revenue and the cost for those years. So part A asks us to use cubic regression with x equals 4 corresponding to 2004. So I need to switch to my calculator view. Regression means to put the list into the calculator. So I've already entered the list to make this a little bit faster. And I need to do 2 cubic regressions, one with the revenue data, which is list 1 and list 2, and then the cost data, which is with list 1 and list 3. So once you have your data input in your list, you're going to quit out of that. And then you're going to do the stat calculation. So let me make sure my diagnostics are on first. And then I'm going to do stat. Over to the calculate menu, I want cubic regression, which is option number 6. It is set to use list 1 and list 2. So I'm going to write this down on my paper using 2 decimals for each of those values. So 551.09x cubed minus 12,600.99x squared plus 82,827.73x, and then plus 7,001.80. Now to get my cost function, I go back into stat, over to calculate, again, cubic regression, but this time I need to change my Y list to be list 2. So notice on your calculator above your numbers 1, 2, and 3, and 4, 5, and 6, you see L1, L2, L3. I need to use L3. It's blue like my second button, so I'm going to push second, the number 3, to change my list to be list number 3. And then I get my cubic regression for the cost function. So the cost function is 885.50x cubed minus 21,438.36 x squared plus 154,283.34 x, and then minus 166,073.76. So before I go back and show what I've written on my notes page, I'm going to go ahead and do part B, which asks us to plot both sets of data on the same graph. And this is just a practice skill that our calculator can do called a stat plot. Notice above the Y equals button here, it says stat plot. So I'm going to push second, Y equals. And number 1 says plot off. So I'm going to push enter there to go into the menu. And I'm going to put my cursor on, hit enter, which turns that stat plot on. We're just going to leave it on the regular stat plot. It has list 1 and list 2 and a marking. So I'm going to quit out of that. And I'm going to go back into stat plot, second Y equals, and turn on the second one, plot 2, turning it on. I'm going to change my Y list to be list 3, just like we did in the calculation earlier. I'm going to push second, number 3. And then I'm also going to go down and change the mark to be one of the other 2 choices for this stat plot. Once you have the stat plots ready, you have to do zoom, the zoom button in the top middle, and it's option number 9. Option number 9 is zoom stat, and that's going to plot so that you can see both sets of your data together. So I made the revenue, the little blocks, and the cost, the plus signs. So remember that wherever cost is above revenue, you're losing money. Where revenue is above cost, you're making a profit. So I could get a rough estimate here for part C. Let me go back to my notes page. So part B is our calculator plot, just to kind of get an idea of where profit began. And then for part C, we're going to find our profit function and see for what years it was profitable. So remember, the profit function is the revenue function minus the cost function. So I'm going to copy those down from above. And remember, when you subtract that cost function, you would need to put it in parentheses. So every bit of that function gets subtracted, not just the first term. And when I combine like terms on that, I get a profit function of negative 334.41x cubed plus 8837.37x squared minus 71 455.61x, and then plus 173,075.56. So you could do a regular graph of that function. You could use information from the table above. Remember that this is profitable whenever our profit function is greater than 0. So I'm going to show you how I get this in the calculator in a second. But if you'll look in the calculator, this happens in 2004. So 2004 and 2009 to 2013, sorry. Okay, so I can look up here and see cost is less than revenue, cost is less, cost is less, cost is more, sorry. Cost is more, cost is more, and then we go back to where cost is less. So the way that you could look at this in the calculator, I'm going to turn my stat plots off. And I'm going to go into y equals and type in my profit function. I didn't get an X. And I'm just going to look at the table. So I'm going to push second graph. Oh, I didn't use the negative sign. I used the subtraction sign. And as long as profit is positive, that's when it's profitable. So we started in 2004. So even though these other years are positive, we're not worried about anything until 2004. And then we have some negative values. And then we see again in 2009 through 2013, our profit function gave positive values.